So we're going to start out, we're going to look at the limit as x approaches 0 of absolute value of x. And we want to show that that limit is going to equal 0. Well, to start out, if we think about the graph of absolute value of x, probably graphically you could think about it and pretty easily see that the limit of it is 0. But we're going to show it algebraically. When you have an absolute value, we need to think of it in terms of a piecewise function. If x is going to be less than 0, we're really working with the graph of negative x. Because the slope is negative 1, it has a y-intercept of 0. If x is greater than or equal to 0, we are really working with positive x that has a slope of positive 1 and has a y-intercept of 0. So we'll now look at our left-hand and right-hand limits. So the limit as x approaches 0 from the left of absolute value of x is really the same as saying what is the limit as x approaches 0 from the left of negative x. Well, that's just going to end up being 0. You could do that with direct substitution. And if we now want to look at the limit as x approaches 0 from the right of absolute value of x, we're really going to be looking at the limit as x approaches 0 from the right of positive x. Well, again, when we do direct substitution, 0. Therefore, we can conclude, because the left-hand limit and the right-hand limit are the same, the limit as x approaches 0 of absolute value of x is just, in fact, 0. So now we're going to do the limit as x approaches 0 of absolute value of x over x. Well, we're going to use, again, the fact that we want to think of absolute value of x as a piecewise function. So when we look at x approaches 0 from the left, we're really going to be working with negative x over x, because that's what absolute value of x was when we came from the left. And when we work with x from the right, we're really going to be looking at positive x over x. Now this simplifies to just negative 1. Since that's a constant, it's just negative 1. This here also simplifies to positive 1. Since it's just a constant, that limit will be positive 1. And we can pretty clearly see now that the left-hand limit and right-hand limit are not the same. So therefore, the limit as x approaches 0 of our absolute value of x over x does not exist. So now we're going to look at a piecewise function. We're going to see our limit as x approaches 4 of f of x. Well, really, when we do the limit as x approaches 4 from the left, we'll want the section where x is less than 4. So we'll really be doing it for 8 minus 2x. And when we want the limit as x approaches 4 from the right, we really want to be doing that for when it's greater than 4, so that would be the square root of x minus 4. Well, we'll always try with direct substitution first. In that top one there, when we're approaching from the left, this will just become 8 minus 2 times 4, which will just give us 0. This will become square root of 4 minus 4, which will also give us 0. So therefore, because they are the same thing, the limit is going to exist. And our limit as x approaches 4 of f of x will in fact just be 0, because the left-hand limit and the right-hand limit were equal to that. And there's a visual of that. There was our left hand, the line part, and the right hand, the square root part. They are, in fact, both converging to the y value of 0 from both the left and the right. So now, two theorems. This first theorem, if we know that a function is going to be less than or equal to some other function, at all the x values near some other x value we'll call a. But it doesn't have to be at a, because we're going to think of it in terms of a limit. And we know a limit is just as we approach a value and not necessarily at that value. Then what we can conclude is the limit of f of x as it gets close to a has to be less than or equal to the limit of g of x as x approaches a. And that makes sense if the function values are being less than or equal to the other function values, then the limit should be less than or equal to it. Now, an extension of that is what's called the squeeze theorem. Instead of just having one function less than or equal to another function, think of this as for g of x, what if we had a function that stayed in between two functions for all the function values? And then what if also we knew the limit of the one on the left and the limit of the greatest one, the one on the right, were both equaling the same thing? So L is just some number. So maybe both those limits as x approached a were 5. Well, then what we can conclude is that these limits must also have to be, say, 5 or whatever number that had to be. So if those outer limits, the left hand, right hand there, the f of x and h of x are going to the same thing, then g of x must also go to the same thing because g of x was staying in between them. And a nice visual of that is something like this. So h of x is always greater than or equal to the other ones. F of x is always less than or equal to the other ones. So g of x is always staying in the middle between them. So if h of x and f of x are both converging to the same thing, g of x must also converge to that same thing. So that's the squeeze theorem. It's squeezing it together, you can think of it as. So now we'll try and apply that. So we're going to prove here that the limit as x approaches 0 of x squared times sine of 1 over x is going to in fact equal 0. And to do that, we'll start with something we know. We know that every sine graph stays in between -1 and 1 for its range. So we know that -1 is less than or equal to sine over x, which is less than or equal to 1. Because we know sine 1 over x has to stay in between those. So what we're going to do is we're going to multiply everything by x squared. Now, x squared has to be positive because you're squaring it. So therefore, we don't have to flip our sign or anything. And we'll now get negative x squared less than or equal to x squared times sine of 1 over x less than or equal to x squared. Notice now in the middle, we have the function that we really want to work with. We are now going to look at our limit as x approaches 0 of those two outer functions. So let's look at the limit as x approaches 0 of minus x squared. Well, if we think of what the graph of negative x squared looks like, it's a parabola opening upside down. So as we approach an x value of 0 from both the left and from the right, our y values approach 0. If we do our limit as x approaches 0 of positive x squared, the graph of positive x squared is a parabola opening up. So as x values approach 0 from both the left and right, the y values go to 0. So this limit is also 0. Since we have shown that our low bound and our upper bound as x approaches 0 both have a limit of 0, we can say by the squeeze theorem we now know x squared sine 1 over x must equal 0. And it's important that you say by the squeeze theorem. All right, so we'll finish off with a couple of extra examples. So first here, we're going to try and evaluate this limit. We always try and do direct substitution first, but if we do direct substitution here, notice we'll get a 0 in the denominator. So we got to figure out some other algebraic method how we could evaluate this. We've got radicals, so our common method we use is conjugates. So we are going to multiply top and bottom by the conjugate of that numerator, which would be 3 plus radical 3 plus x plus radical 3. And we'll multiply that top and bottom, and the reason we can do that is it's just really a fancy version of 1, and when you multiply by 1, it doesn't change the value of anything. So this will become the limit as x approaches 0. In the numerator, the whole reason of multiplying by conjugates is the inside and outside terms will add to 0, cancel each other out, so we'll be left with 3 plus x minus 3. Now, if that second part had more than one term, we'd have to distribute the negative, but it didn't here. Remember, never multiply that x out on the bottom, because eventually we're hoping that'll cancel out. The 3 and the negative 3 add to 0, so we'll have now the limit as x approaches 0 of x over x times our conjugate. The x's cancel out, and now we have the limit as x approaches 0 of 1 over square root of 3 plus x plus square root of 3. This is now something we can do with direct substitution. So we'll sub in the 0. We'll have square root of 3 plus 0 plus square root of 3. And you can either write it as 1 over square root of 3 plus square root of 3, or that's the same as saying 1 over 2 square root of 3. And one last example to finish off the video. If we try to do direct substitution in this limit, we again get 0 in the denominator, so we've got to find some other algebraic method to be able to evaluate this. Well, let's multiply that out, that 4 plus h squared. That's really 16 plus 4h plus 4h plus h squared, which is really 16 plus 8h plus h squared. So we'll rewrite that over here as the limit as h approaches 0 of 16 plus 8h plus h squared minus 16 all over h. The 16 and the negative 16 add to 0, so we now have the limit as h approaches 0 of 8h plus h squared all over h. The h's divide out, and that'll leave us with 8 plus h. This is now something we can do with direct substitution, so this will become 8 plus 0, which is just 8. The limit goes away, keep in mind, when you do your direct substitution. The limit should be carried through each step until that direct substitution is done. That's it for this video. We'll see you next class period.